If you were to summit Mount Everest today, you'd find something completely unexpected under your boots. The rock at the very top of the world is limestone, packed with fossils of trilobites and crinoids, creatures that lived at the bottom of an ocean over 400 million years ago. To understand how the ocean floor ended up almost 30,000 feet in the air, we have to rewind about 55 million years to the Eocene epoch. Back then, the Earth was in a deep greenhouse state, with a global climate that was warm, wet, and humid. In ancient Asia, the landscape looked completely different. The space where the jagged peaks of the Himalayas now stand was covered by the Paleo-Tethys Ocean, bordered by lush tropical forests filled with fig and ironwood trees. As the Indian subcontinent drifted north and crashed into the Eurasian Plate, the resulting tectonic uplift thrust the ocean floor miles into the sky. This event initiated a series of geochemical changes that would eventually end the planet's greenhouse era. Fast forward to the Miocene epoch, about 23 million years ago, and the Earth's thermostat plummeted. The warm, humid conditions that defined the globe rapidly gave way to a much colder, drier reality. This chart shows the correlation between that drop in temperature and a sudden decrease in atmospheric carbon dioxide. With less CO2 to trap the sun's heat, the global greenhouse effect weakened. Carbon dioxide doesn't vanish on its own. To locate the sink that drained the atmosphere of its heat-trapping gases, scientists began investigating the specific consequences of the tectonic collision in Asia. When the Indian and Eurasian plates collided, the immense pressure buckled the Earth's crust upward, creating a jagged wall of rock reaching 4,000 meters high. This towering new landmass acted as a physical barrier to moisture-heavy winds coming in from the ocean. As the air was forced upward against the peaks, it created a massive rain shadow. At high altitudes, the air expanded and cooled, causing water to condense out as rain. This process generated an intense, relentless weather system on the windward side of the mountains, the monsoons. The tectonic crash engineered an extreme weather system, providing the ingredients for a planetary-scale chemical reaction. It starts high in the sky. As a raindrop falls through the atmosphere, it absorbs small amounts of carbon dioxide floating around it. That dissolved CO2 converts into carbonic acid. By the time it hits the ground, it is slightly acidic. Scale this up. Picture millions upon millions of gallons of this acidic monsoon rain continuously battering the towering, freshly exposed rock faces of the growing Himalayas. This triggers a process called chemical weathering. The carbonic acid in the rain reacts with the mountain rock, dissolving it and binding the trapped carbon into new bicarbonate ions. The sheer volume of fresh rock pushed up by the tectonic plates, lashed by acidic rain, accelerated this process to a level that shifted the chemical balance of the entire atmosphere. Those bicarbonate ions were flushed off the mountains and into an increasingly complex network of rivers, carving deep valleys as the carbon-rich water washed out to sea. Once in the ocean, these ions were consumed by marine organisms, like diatoms, which used the carbon to build their hard, protective shells. When those organisms eventually died, they rained down onto the seafloor, locking the carbon away in deep ocean storage. The Himalayas functioned as a continuously running planetary carbon scrubber. By physically pulling heat-trapping gas out of the sky and burying it at the bottom of the ocean, the mountains chilled the globe. By disrupting the global carbon cycle, the Himalayas lowered global temperatures and reduced the moisture-holding capacity of the atmosphere. The impact reached as far as Antarctica. As the world cooled, the temperate vegetation died off, and it was locked into a permanent deep freeze. Because cold air holds less moisture, the planet also became significantly drier. In North Africa, the humid forests that once thrived there could no longer be supported by the dwindling rainfall, eventually giving way to the expanding sands of the Sahara Desert. The rise of these mountains in Asia directly contributed to the glaciation and desertification of continents thousands of miles away. This climate shift forced a transition for life on land. As carbon dioxide levels dropped, the thick tropical and subtropical forests across Europe, Africa, and North America began to disappear. In their place, C4 grasses took over. These plants are uniquely adapted for arid environments with low CO2, and they quickly covered the Earth in vast plains. These wide-open spaces created a new set of selection pressures. Grazing mammals like early horses no longer needed to navigate dense brush. Instead, survival favored size and speed to cover great distances and spot predators on the horizon. These low CO2 plains also paved the way for massive flightless birds like ostriches to dominate. We often think of mountains as vertical, static features of the landscape, but the Himalayas prove geology is a global force. By rewiring the atmosphere, they built the roof of the world and dictated the evolutionary path of life on Earth.